So it's my glad pleasure to welcome everybody to this, our first lecture in this new Lumer series. And actually, it's a continuation of the lectures which were held with the previous course program. Yes. And it's also my great pleasure that to see that so many of you attend these lectures. I hope that it will continue in the future. Yes. And our first lecture is Serge Nicaise from the University of Valenciennes. And actually, uh, I don't know how to count these 40 years in spectral theory because it appears that he is not yet 40 years in spectral theory because he defended his thesis on the 21st of February 86. So it means that there are a few days left until full full participation in spectral theory. Yes. So and okay. Anyway, so he was almost all his life he was a professor in Valenciennes, and he was a head of the laboratory Keramas, I think, yes,
Mhm. Exactly.
for many years, yes, and he has about 30 PhD students. He has supervised 30 PhD students, and he's a specialist in spectral theory, PDEs on the non-smooth domains, and so on. And he is also famous for Nicaise inequality. Yes, and I can say that I'm also happy because to tell you about this Nicaise inequality because a few years ago we have proven it and we were extremely happy to that we managed to prove something like this. And then later we found out that it has been proven earlier. So it's yeah, but still our proof is not so bad. But what is interesting, we found out that it was not only we who reproved it, there was another person who also managed to prove the same inequality. So I think it shows how important it is. Yes, and I think that Serge will speak about it. But
Mhm.
what is more important for this series is that he was a student of Günther Lumer. Therefore, he will also tell us a few words about his supervisor. So please.
Thank you, Pavel, for the introductions. First of all, I'm very proud to have been chosen as first speaker of this Lumer series. So, of course, I warmly thanks the head of the the working group one, Pavel, Marketa, and Matthias, for the invitations. And as he said on the demand of Pavel, I will start with some few words about Gunther Lumer. Okay, so the outline of my talk is the following one. After some words about Gunther Lumer, I will start with some motivations why we want to study spectral analysis on graphs. Then I will introduce the Laplace, what I call the Laplace operators on graphs. Then I will give some characterization of the spectrum. So I also speak about some spectral gaps. So in that sections, I will speak about my Nicaise inequalities. Then I will speak also about some asymptotic behavior of the eigenvalues, included Weyl's formula, and then I will end up with some recent extensions to other type of problems. Yeah. Okay, so about Gunther Lumer. Actually, he was born in Frankfurt in 1929 and he passed away in Brussels in 2005 after three cerebral attacks. To escape Nazism, actually, his family left Germany in 1933 for France. That's the reason he was very good in French languages. And then for Uruguay in 1941. He graduated as an electrical engineer in 1977, but had already a lifelong patience for mathematics and actually was already working in the research group of Almos in Montevideo. Then he got a Guggenheim Fellowship to study at Chicago, and where he received his PhD in mathematics in 1979. His supervisor was Kaplansky. And then he becomes professor in UCLA, Stanford, Washington, and then finally Mons in Belgium. So his main research topics were functional analysis. Oh, sorry, I didn't see my slides anymore now. Do you see it? Ah, yeah. So functional analysis, PDEs, and evolution equations. His most famous result is the so-called Lumer-Phillips theorem that was published in 1961. He is probably the first who performed a pure mathematical analysis of second-order differential operators on metric graphs. Actually, he has 3 papers published in 79 and 80s, but then he left the hands, in a sense, to youngest persons, like Felix Ali-Mehmeti. He got his PhD in 1977, 87 in Mainz, in Germany. Joachim von Below in PhD in 1984, and in Tübingen, and myself, as Pavel said, in 1986 in Mons. And of course, afterwards, with a much broader development that you know, certainly. Yeah? And finally, by his inexhaustible energy and his love of mathematics, in 1990, he was able to develop the fields of evolution equation and semigroup theory via some support of the European community. And with this support, he organized the international conference and got some large-scale project, or developed large-scale project. So here is a small summary of his life. Yeah. Okay, so now the motivations to study the spectral property of the Laplace operator is quite large. I can mention as application the asymptotic behavior of diffusion processes, control theory and stabilization, or asymptotic stability of small standing waves for nonlinear Schrödinger operator on graphs. So the goal of my talk is today to recall some old and even more recent results on finite graphs, and mention some recent results for infinite graphs and indefinite operators. So the main tools that are used are the use of fundamental solution of the related ODEs and some algebraic manipulations, take advantage of the min-max principle, and also the use of the knowledge of the eigenvalues in some particular cases, mainly when you put Dirichlet or Neumann boundary conditions at the end of the edges. So let me start with some notations. So for me, mainly in the talk, I considered a finite and connected graph with the edges will be denoted by AJ. They are identified with an interval of finite length, LJ, and the number of edges will be denoted by n sub e, it's finite, and we denote by v the set of vertices. And nv is the number of vertices that is also supposed to be finite. So without loss of generality, I can assume that there is no loop made of one edge, which means that if you have, for instance, as the tadpole like here, so the tadpole could be considered as a circle with an attached intervals, but to avoid a loop like this, we divided this loop by 2 intervals and add an artificial vertex V3. Yeah, so for a vertex V, I denote by EV the set of edges of indices of edges having V as endpoint. I denote by Vx the nodes for which the degree of V is 1, and I denote by V internal the remainder of a set of vertices. And finally, I suppose that the set of external vertices is divided in 2 subsets, distinct subsets, V dir and V neu, and clearly on V dir we will consider Dirichlet boundary conditions, and on V neu, Neumann boundary conditions. Of course, one of these 2 sets can be empty. So here are 2 illustrations of graphs. Yeah, so this is quite natural for the majority of the followers. So now let me introduce the Laplace operator on the graph. So for k, positive integer, I denote by phk. Ph means piecewise hk's, subordered spaces, as the direct sum of hk on all edges. So mainly I use it for k equal 2, but anyway. And then I can define the Laplace operator with Dirichlet and Kirchhoff boundary conditions as follows. I denote the domain will be the set of functions that are piecewise in H2 of the graph. They are supposed to be continuous on the graph. They are supposed to be zero on the vertices belonging to V dir. And then for the other vertices, V in V1 or V9, I consider that the sum of the normal, the exterior normal derivative of UG at V, the sum of for all J, arriving to the vertex V, that this sum is zero. Yeah, so for an exterior node, of course, you get there is only one edge, and then you have Neumann boundary conditions. And for the interior nodes, we have the so-called Kirchhoff boundary conditions. And then, of course, the T of U is defined as minus the second derivative of U on the edge J and for all J in A. Yeah. And it is well known that this operator is self-adjoint, non-negative, with a compact resolvent, hence it has a discrete spectrum. Okay, so now I wanted to speak a bit about the characterization of the spectrum. Then I first introduce some notations. Mainly I need to introduce three matrices. So the first one is related to the case where for positive real numbers lambda, the sinus of square root of lambda Lj is different from 0 for all j in A. And then I can introduce the matrix D of lambda of size, the number of interior nodes and Neumann nodes. And this is defined like that. If you take two vertices that are different but that are joined by the edge J, then on the value of dVW is given by the inverse of the sinus. If V is equal to W, you have this sum here, and otherwise it is zero. Yeah. So this matrix can be computed explicitly if you know the graph and the length. Yeah. So this is for the first. This matrix is used for the first characterization of the spectrum, and for the second one, I introduce another set of matrices, and for that purpose, in a sense, I introduce for one edge, I introduce two arcs that are of opposite orientation that I name J and minus J, and I introduce the set of arcs that I denote by a bar. This is a notation that I introduced in my PhD thesis, actually, which is the set made by G and minus G for G in E. And finally, for J in E, I denote by E of J the initial extremities of the edge AJ, which means that if the vertex corresponds to 0, I denote it AJ, and if the vertex corresponds to the final extremity LJ, I denote it by FJ. And for the opposite edge, I denote by E of minus J the final vertex of J, and conversely for the final value of minus J. So finally, I can introduce two matrices, D and M, which are the size is 2 times the number of edge. And for D, it's a diagonal matrix where on the diagonal you put the length of the edge J or the opposite arcs. And for M, well, I don't go to the details, but it is defined like this. Yeah, it's a bit technical, but this is again this matrix M can be built it up if you know the graph, and that's it. Yeah, nothing more. Yeah, good. Then the first characteristic, or well, I heard from Pavel that you call it now secular equations, is the following one, and it was mainly due to von Belo published in '85 for the case where V dir is empty, And I extend this to the case where the VD could be different from the empty set, and this appeared in my PhD thesis in '86, and it says the following one: 0 is a simple eigenvalue of t if and only if VD is empty, and if you fix lambda, a positive real numbers lambda, such that sinus or square root of Lj is different from 0 for all j, then lambda is an eigenvalue if and only if the determinant of the matrix D of lambda is equal to 0. Yeah, let me give a hint of the proof. Yeah, for 0, it's quite easy. If you consider u in the kernel of t, then of course the second derivative of uj is 0 on each edge, so it is linear. So it's on this form with some constant aj and bj. And then by Green's formula, you directly see that the integral of the derivative squared is 0, so aj is 0. And then by the continuity of u, so this means that ug is constant on each edge, and by the continuity, u is constant in the whole graph. And if vd is empty, u can be constant, otherwise it is 0. Yeah? So for the second case, the trick is to write, if you take, so the trick is you are looking for a vector, an eigenvector uj, or u of eigenvalue lambda. So on each edge, you want to write uj as linear combination of fundamental solution of the ODEs. And the trick is to use these two fundamental solutions and these ones and these ones. And the trick is that the first here, or the second one here, is a function that is equal to 1 at x equal to 0, and it is 0 at Lj. And conversely, this one is equal to 0 at 0, and it is 1 at Lj. Yeah, and of course, then any solution of minus u second is equal to lambda u is a linear combination of these two ones with some parameter aj and bj, and then of course clearly by the continuity of u, you will have that aj is equal to uv if v corresponds to is identified with the end of the interval aj, and bj is u of w if w corresponds to 0. So this means that you know the eigenvectors if you simply know the value of u at the nodes, and the value of at the nodes are the remaining unknowns. And of course, clearly by the Dirichlet boundary conditions for vertex on the Dirichlet sets, this value is 0, and then it remains only the value of u at the interior and Neumann nodes. And by some manipulations using the Kirchhoff conditions, you can check that if d of lambda of u of v of the vector u of v is equal to 0, and then a non-trivial solutions exist if and only if the determinant of d of lambda is 0. That's the proof mainly, yeah? Okay, so let me go to the second characterizations. And one of the drawbacks of the previous theorem is that the case when sinus of square root of lambda Lj is equal to 0 for some j is quite delicate to manage. And this was the motivations to prove another theorem that was proved by Jean-Pierre Roth, I think, for in the case VD equal empty again in the preprint in '84, and it's in my PhD again in '86. I never published it in a paper. And it says that lambda, a non-negative real numbers lambda is an eigenvalue of t if and only if 1 is an eigenvalue of the matrix E square root of lambda d m, or equivalently if this determinant here is equal to 0. Yeah. And again, how do we prove this? This is simple. This is quite simple. You again write U as a linear combination of two fundamental solutions, and here I use these ones. So I write uj equal aj times a of this one plus a minus j of this one. And that's the reason of the introduction of this g equal to a bar, because this is quite comfortable in the argumentations. Yeah. And you see then you can use only a family of parameter aj with j in a bar. Yeah. And then you use the continuity and the Dirichlet and Kirchhoff boundary conditions and perform some algebraic manipulations, and then you arrive to these equalities And then again, with aj is an unknown vectors. And then again, a non-trivial solution exists if and only if the determinant of this matrix is equal to 0. Yeah? So the drawback is the size, because it's quite larger than before. But the advantage is that it is valid for all non-negative real numbers. And as we will see in the next slides, it's easily extended to other boundary conditions. Yeah. So because there are similar approaches for the Laplace operator, for instance, for general boundary conditions, it was proved similarly for more general boundary conditions like delta conditions, for instance. But it was proved by Kotrishkin and Schrader and Bolte-Endres in 2006 and 2009, and also by Plumer and Matthias in 2001, where they proved that lambda is an eigenvalue of T if and only if the determinant of a certain matrix is 0, but the size here is the number of vertices plus 2 times the number of edges. There are also similar approach for the magnetic Schrödinger operator. So the magnetic Schrödinger operator is an operator of this kind. So it's E, the complex number E, d over dx plus aj squared plus qj. Let's say they are constant for the moment here, and you consider this on each edges, plus some boundary conditions that comes from continuity and some integration by parts, a sort of Kirchhoff boundary conditions. And a similar characterization was proved by Kotos and Smilansky and Alan Berkolaiko for the case qj equal to 0. And for qj different from 0, you can find a proof in the book of Pavel. Yeah? Good. So now let me speak about some spectral gaps. So let me start by standard, let's say, or classical spectral gaps, and which was, at least for me, the motivations to prove the spectral gaps for graphs. They are the following one. So you have two categories. The one is the so-called Faber-Kranz inequality, and the second one, Schrödinger-Weinberger inequalities. And what does it say? Yeah, so you take a domain of Rd, d larger than 2, and then you denote by lambda 1 of omega the first eigenvalue of the Dirichlet Laplacians, which means the Laplace operator with Dirichlet boundary conditions, and by mu2 of omega the first positive eigenvalue of the Neumann Laplacian. So the Laplace operator with Neumann boundary conditions on the boundary. Yeah? And if you consider a ball of Rd for which the volume of the ball is the same than the volume of omega, then lambda 1 of omega is larger than lambda 1 of b. And you have equality if and only if omega is equal to the ball up to a rigid transformations. Yeah. And for Schrödinger-Weinberger, it's for Neumann, and it's a reverse inequalities. It says that for Neumann eigenvalues, you have that the eigenvalues, the second positive eigenvalue of the Neumann Laplacians in omega is bounded from above by mu2 of b, and with equality if and only if, of course, omega is the ball, up to a rigid transformation. Yeah. So, and then it was my motivations to prove similar estimates for graph. Yeah. And actually, Schrödinger-Weinberger inequality is wrong for graphs. But I succeed to prove the reverse inequality, so the Faber-Kranz inequality on graphs. And as Pavel said, now it's called or named Nicaise inequalities, since I think due to Pavel or Delio, or I don't know exactly who is responsible of this name, but at least thanks you for the nomination. Yeah. So assume that assume first that the set of Dirichlet vertices is empty. Then if you consider lambda 2 of j, the first positive eigenvalue of t, and if you denote by L, so the length of the graph, meaning that you take the sum of the length of the edge, then lambda 2 of j is larger than pi squared over L squared. And this estimate is optimal since for j equal the interval 0L, with Neumann boundary conditions, we have equalities. And as Pavel said, these inequalities was proved. So I prove it in my PhD thesis, and I published it in 1987. And Friedlander and Pavel and Nabokov proved it independently, in a sense, quite later on. Yeah. And let me give a sketch of the proof, because it's not so hard in a sense. So my proof is based on Eulerian path technique. And this is exactly the way Pavel and Nabokov proved. And Friedlander used another method which is named the symmetrization technique. Yeah. So how to do that proof? Yeah, you see, it's you can write it in one slide, so it's not so difficult. Yeah. So you take an eigenvector u associated with lambda 2, and so you take it of norm 1, and then by the min-max principle, you know that lambda 2 of j is the integral of the derivative of u squared. Yeah. And what we do is that we build, by exploration of the graph, we build a circuit made of arcs that I denote E1, E2, E2n, arcs of j in the sense that I denoted before, and you run the full set E bar. So these arcs completes the set E bar. And the circuit goes 2 times on each edge, 1 time in one direction and 1 in the opposite directions. So here is a pictures. Yeah, that comes from my PhD thesis. Yeah, so this is the graph in black. Yeah, this is a tree. Yeah, and then how do you build it up the circuits? You start from this vertex, you go in this way, then you go in this way, you run like this, and you continue in this way, and at the end you have performed you have made you have built it up your circuits, and as you see, for this edge you have run in one direction and then in the other directions here, and this is the same everywhere. And if you have a circuit like here, then you cut it artificially to so you cut any circuits to render your graph as a tree. Yeah. Okay, so with these circuits, you are able to build a mapping that I denote by R from the circle C of length 2L into J, so that U composed with R belongs to H1 of C. Yeah, this is quite, in a sense, quite easy to see. You take this and you enlarge it to make a circle. Yeah, this one you go here, and then you build it up a circle. Yeah. Okay, so, and what is the main point is that if you compute the derivative of u composed with r prime, take the square and integrate on the circle, you notice is due to the fact that you goes 2 times on the edge, one in direction and on the opposite directions. It's 2 times the integral of the square of the derivative of u, and the same for u. And the main trick is that u composed with r remains of mean 0. Yeah? U is of mean 0 here, of course. Yeah. Then, of course, by these equalities, you see that this is equal to that. But the min-max principle means that the second eigenvalue of the Dirichlet problem on the circle is equal to this quantities, this minimum. But of course, this minimum, because this one is of norm 2, yeah, here. So the 2 is here, the norm of the square of the norm of the L2 norm of u composed with r. Then this quantity is larger than this minimum. Yeah, and then since this value is equal to p squared over L squared, the proof is over. Yeah, so it's quite easy. I mean, okay, so that's for the first spectral gaps. The second spectral graph is quite similar. It concerns the Dirichlet case. It means that if you assume that the set of Dirichlet nodes is non-empty, then the first positive eigenvalues of T is bounded below by p squared over 4L squared. And the proof is exactly the same, except that since you have a Dirichlet nodes, U composed with R belongs to H10 of the circle. And then otherwise it's the same proof. And of course you lose the mean value 0 property, but we don't need it for the first positive eigenvalue in the Dirichlet case. Yeah. Okay, and this again, this estimate is optimal since for the intervals with Dirichlet boundary conditions at 0 and Neumann conditions at L, we have equalities. Good. So let me now pass to the asymptotic behavior of eigenvalues. So here I assume this is a result that I also prove in my PhD thesis. Assume that the lengths are 1 for all j. Yeah. So and denote by lambda n the spectrum of lambda n, n in n the spectrum of t. Then if the set of Dirichlet nodes is non-empty, you have these bounds that lambda n is bounded by n over L plus 1 squared p squared for all n actually, and for n large enough, you have the lower bounds that lambda n is bounded below by n over L minus 1 squared p squared. And we have a similar estimates for if v dir is empty, but then you have to make a shift of 1 because, of course, we have the zero eigenvalue to exclude it in a sense. Yeah. Okay, and how do we prove this? This was mainly proved in the 80s. It was it is mentioned in my paper, and also Felix Alimemeti proved these estimates. And in my case, actually, I prove it using the first theorem and some algebraic arguments for managing the eigenvalue k squared p squared. And you count the number of eigenvalues, and at the end, you find these bounds. Yeah. And on the contrary, in the paper of Felix in 86, he used the min-max principle by comparing the spectrum of the Laplace operator with where you put Dirichlet boundary conditions at all extremities of the edges or Neumann. And by the min-max principle, you have these bounds. Yeah. And by this, since these families is explicitly known, and this one as well, you find the results. Yeah? Good. But there are also similar results for the general situations. They are more recent. Yeah. So this is a summary. I hope I am not wrong. If you consider the case where Vd is empty, then we have these bounds that lambda n for all n is bounded below by n squared p squared over 4l squared, and it is bounded above by the same factor multiplied by the number of h squared. And the lower bound was proved by Friedlander using symmetrization technique, and the upper bounds, if I'm not wrong, was proved by James Kennedy, Pavel Kurasov, Malenova, and Delio in 2016. Yeah. Good. So now let me continue with Weyl's formula. So first, I would like to recall the standard Weyl's law that describes the
Serge, you're frozen. I think, yes. Is it correct?
It's frozen for me also.
Hello, quarantine. So, Delio, you are watching that. He's coming back.
I'm writing to him.
No, but see, if you give a lecture, you don't read your emails usually. You see, when I wanted to make a comment when he was speaking, but because when I look at this list of years when Nicaise inequality was proven, I thought that it's time to prove it once more.
Okay, I'm back.
Sorry.
There is a
Welcome.
problem, Wi-Fi connections probably, yeah? Sorry, but now I have to be back to maybe partager. Yeah. Do you see it now?
Yes, we can see. And
Okay.
we stopped hearing you precisely when you started to speak about Weyl's law.
Yeah, okay, perfect. Okay, so concerning Weyl's law, let me first, let's say, recall the standard Weyl's law that describes the asymptotic behavior of eigenvalues of the Laplace-Beltrami on operator on domains or even on manifolds. And it was actually discovered by Weyl's. What is this? No, that's correct. By Weyl's in one century, more than 1 century ago, for the Laplace operator on domains of Rd, actually for d equal 2 and 3, and with Dirichlet boundary conditions on the exterior boundary. And in particular, he proved that the number n lambda of Dirichlet eigenvalues strictly smaller than lambda satisfies this limit, and in particular, where omega d is the volume of the unit ball, and in particular, this implies that that the limit of lambda n over n to the power 2 over the dimension is a constant given by this expression. And for d equal 1, you recover that lambda n behaves like n squared. Yeah? And actually, I proved Weyl's formula for graphs, and by showing that that if n lambda is the number of eigenvalues smaller than lambda, then n of lambda divided by square root of lambda is equal to L over pi, the limit, yeah. And actually, this you can prove this by essentially use the theorem 2 that I mentioned, so the second secular equations. But it can also be used by using the estimates from Ali Mehmeti, that you have the lower bound and the lower and upper bounds with respect to lambda, the Dirichlet and Neumann eigenvalues. Yeah. Of course, similar results were proved more recently. For Schrödinger operator, it was proved by Carlson and Piwowarczyk. And you can find the same results for the magnetic Schrödinger operator in the book of Pavel. Okay, so now let me end up with some recent results. So let me start with infinite graphs with finite volumes. Quite recently, Duffel, Kennedy, Delio, Plumer, and Matthias as considered infinite graph with finite volume. They give some criteria to guarantee that the operator has a discrete spectrum, and they prove some lower and upper bounds of the eigenvalues. For instance, they show a similar estimate that I showed before for finite graph, but here for locally finite and connected graph with a finite volume L and with only Neumann boundary conditions on the exterior boundary and nodes, let's say. And they prove the upper bounds as before, that lambda n is bounded below by n squared p squared over 4 times the length squared. And as far as understood, this is proved by combining the symmetrization techniques from Friedlander with the Correa formula used by Bond-Levy in the context of graph. And this is where all these estimates for all n are optimal. And finally, for what about indefinite operator, motivated by, let's say, quite recent paper of Amari, Ducas, and Gontier, and also a more old paper of Hussein, where they consider only some particular case of indefinite operator. I wanted to study a general indefinite operator. And what is this? This is an operator, T of u, of the form minus kj uj prime prime for all edges, where kj can even be functions, but the point is that kj can be positive on some edges and negative on some edges. Yeah, and what is the domain of this operator? You take the functions that are piecewise h2, continuous, 0 on the Dirichlet nodes, and you have a sort of Kirchhoff conditions. But here you see that up here, okay, let's say kg is constant here. you add this factor kj. So it's a sort of Neumann of Kirchhoff conditions, but the factor in front of the normal derivatives is changing of sign eventually. And what I proved is that I proved that T is self-adjoint, that it has a discrete spectrum, but actually if there exists at least one positive coefficient and one negative, the spectrum is unbounded in both directions. So you have eigenvalues going to plus infinity and eigenvalue going to minus infinity. And then I give some secular equations, and actually I also prove Weyl's formula. And well, I will stop here and thank you for your attention. Yeah.
Okay. Thank you very much for your lecture. So I was supposed to check the chat, but I didn't do, but there is nothing there, if I understand correctly. So are there any questions or comments?
Oh, I see a lot of uploads.
Yes, there are applause. I would also put applaud, but I don't know how.
Don't worry, don't worry.
Okay. So questions?
I have a small
Corentin,
question.
please.
Sorry, it's Corentin Lénard.
Corentin, yes.
What does Weyl's law look in the indefinite case?
Yeah, that's quite easy. I mean, so let's say that okay. Then I explained it in this way. Can I share again or not? Yeah, where it is here it is. Yeah, so let's go here. Yeah, so assume let's say for simplicity that would be better to explain. Assume that kj is 1 or minus 1, which is the case considered by Hussein, but he didn't prove, I think, Weyl's formula. Yeah, and then you say if kj, so you take the sum of the lengths of the edge where kj is 1. Yeah, so let's call it L plus. Yeah, and then the large eigenvalues. So you have the same. So you have the same formula then here. Yeah, you have the number of positive eigenvalues divided by square root of lambda is L plus over pi. And for negative it's L minus. Yeah, so it's very simple and very nice. Yeah, I'm quite proud about this.
So, but maybe I can add one question. But what happens if k's are not constants?
Yeah, then you have some integrals.
Integrals, yes?
Yes. Yeah. Then you have to take a sort of means of kj, and then L is modified, but it's a constant depending on the length and on the kj. Yeah. Yeah.
Yeah. Marietta has a question. We cannot hear you.
No, we don't. No sounds.
Maybe we take Konstantin then at the moment, yes?
Oh, yeah. Okay.
Konstantin, please ask question.
Can you hear me at least?
Yes.
Yeah.
Okay.
Yes.
So if you mention, okay, thank you for the talk. It's interesting
Thank
to
you.
go back to the topic because I'm not really in for some years, but I'm just interested as in the Weyl asymptotics, there is one of the big topics is the remainder in the next terms. So are there any development in this direction? So
Yeah,
what?
I mean, I never worked on this, but I suppose it's possible because normally, for instance, in the and even in my PhD, you have an explicit formula for the trace of the ETH kernel, yeah, and then from that normally you can I think you are able to prove the next term, yeah, and I think the next term should depend on the number of nodes and the number of edges.
No, actually, I think that there is no possibility for the next term because you see, usually the next term is connected with the potential, and it's some kind of small small perturbation, yes?
Yeah,
But for graphs, you can have pairs of eigenvalues which repeat all the time. So
yeah.
for, for example, if you have a graph with edge length is 1, then the whole spectrum in K scale is periodic, yes?
Yeah.
And then there is no really
Okay, but at least
asymptotic.
okay, but at least from the trace of the heat kernel, you can recover from the spectrum the length, of course, and also the number of nodes, and
Yes,
not
yes.
really, but the sort of difference I don't remember. I think it's the number of nodes minus the number of edges or something like that. Yeah,
Mhm.
yeah, but maybe not from for
Okay.
Weiss formula. Yeah.
So we're happy to see Marietta back. So can you try?
Okay, do you hear me now?
Yes, yes, yes.
Yeah.
Okay, but I need to speak headset. Okay. Uh, my question was just a short question with this Weil's
Mhm.
formula.
Yeah.
Uh, in infinite graphs, what would the L then be?
Hmm. This is probably for Delio question. These questions. Uh,
I thought that you studied infinite graphs at the end.
Yeah, but no. But this was Delio that considered infinite graphs. I considered indefinite operators.
But you consider it on a finite graph, this operator.
Yes, of course, it's on a finite.
Okay.
Yeah. The graph is bounded. Yeah. I don't know
Okay. Then
if Weiss law
I
exists. Or,
misunderstood then. Okay.
maybe Delio can answer to that, but I'm not sure that.
Just what you wrote. I mean, so just graphs for which the total length is finite. So just the sum of
Yeah.
of all edges. Sorry. So sum of all lengths of all edges is finite, and then
Okay.
usually you need to impose some boundary conditions too. In this case.
But do you know if Weiss law is proved for that case?
Actually, we have counterexamples. So we know that there are cases where we have very weird Weyl asymptotics. So there is an unpublished draft together with James and Matthias about that, but let's see. It's an archive, though.
And still, if I may interject, these weird examples you talk about, they have infinite volume. So
Infinite volume, but not finite.
yeah.
But finite, but discrete spectrum.
Yes.
But maybe you can use this comparison principle, yeah, by comparing with the spectrum where you put Dirichlet everywhere and Neumann everywhere, and since the sum of the lengths is finite, maybe we can succeed with this argument.
Maybe if I can, I mean, Joachim here. So in a paper with Patrizio Bifulco, so we studied spectral comparison results on infinite graphs, and we have in the paper there is the proof for if the total length is finite.
Yeah.
So it's exactly what you do. You use this comparison result. It's a bit more work because you have a tail, like a remainder term you have to estimate. So it's not as easy as in the finite case, but it's the same idea.
Okay.
And also there is this example which goes back to Sebastian Endres, like where they have a chain, like basically the half line, where the lengths of the intervals is the harmonic series, so the total length is infinite, and they have an explicit non-standard Weyl law, which has a logarithmic correction. So it's lambda is proportional to n of lambda is proportional to log lambda times lambda. So in other words,
But the volume is infinite.
Excuse me?
The volume is infinite, you say.
Yeah. But the spectrum is still purely discrete. The volume is infinite.
Yeah, exactly. But if the volume is infinite, then there is no Weyl law, so to say.
Yeah.
You cannot say that the Weyl law is wrong because you don't.
Well, it's a non-standard Weyl law. It's I mean it's an expression for the counting function, but it's non-standard. So yeah. And even this is very restricted. They have Dirichlet boundary conditions, and so like basically it's just a chain of Dirichlet intervals. Because you have to count points as a number theoretic problem. It's quite difficult actually. So as soon as, like, if you go to delta, then it's not known, but it's expected, of course, to be somehow same, the leading term, but it's not known.
Mhm.
So Delio had a question, no?
It's kind of maybe the last question for the round. So maybe if there are more technical questions before me, I would be glad to wait a few minutes.
At least I don't see questions. So if somebody has a question, please start. There is something in the chat.
Mhm.
No, these are only things. Okay, so Delio, ask your question, I think.
Yeah, so actually, I have two questions. The first question is an historical one. I know of Lumer's role, as you were mentioning at the beginning, in development of semigroup theory. And I know that he wrote two not so very well known in our community, not so very well known papers in the late 70s about diffusion on networks, so what we now call mapped graphs.
Yeah.
And so this was just before you started working on that as his PhD student. So I was wondering actually what moved you, what made you start thinking of these spectral problems back then? Was it something that came from Lumer? Was Lumer interested in this kind of spectral geometric issues? Or it's just an historical interest?
Yeah. I think he proposed me to study the spectrum. So in a sense, find the secular equations, yeah, something like that. And then so this was a starting point. And then afterwards, I discussed with Luc Paquet, that you know probably, that was also a pupil of Lumer, and he has a permanent position at Mons, and then he supervised me a bit, yeah, quite a bit in a sense, yeah. And then we discussed about these Faber-Kran inequalities and such things, because we wanted to find some new ideas, and then I had the idea so I learned about these inequalities, and then I tried to prove them, yeah. But originally it was simply, I think, from Lumer he asked me to consider the spectrum, yeah, and yeah. And then of course I developed myself on this stuff, yeah.
And my second question is maybe more on outlook side. So, I mean, you have made a beautiful overview of the last 40 years of spectral geometry and graphs. So what do you expect from the next 40 years? What kind of topics would you expect to be interesting in the next 40 years?
Good questions. I mean, of course, we have already made quite a lot of works on this topic. So, yeah, maybe higher order operator are not so well studied in a sense, yeah, on graphs, yeah, like p-harmonic, fourth order operators or systems are not so well studied, yeah. You see, for instance, maybe you know that book of Langnese, Le Guering, Schmidt, where they consider a sort of let's say, beams equations, and these kind of problems were not so well studied for the moment. I mean, with respect to the spectrum, or maybe Weyl's law are not studied, I think. So this could be a possibility, yeah. But it's not for 40 years, yeah. But you start also quite a lot of works on infinite graphs. Yeah, I mean, this is also a quite large program, yeah. And maybe as far as I've seen, you see also consider Schrödinger operator on let's say, when you have some delta conditions with negative coefficients, where you try to find the negative eigenvalues, the essential characterize the essential spectrum. As far why I worked a bit on this, and it seems to be a difficult questions, yeah, or it seems that this implies some difficult questions, yeah, especially when they are, well, if you take constant coefficients, it's quite easy because you can find these well, at least if the principal part is constant coefficients, you can use the Yoast functions or such things. But if you take variable coefficients, it's not so. Then it's not so easy. Yeah. So this could be also a possibility. Yeah. Yeah. But maybe you have better idea than me.
Maybe proving logarithmic Nicaise inequality.
The logarithmic. Yeah. In which sense? Logarithmic Nicaise.
No, this we have to find.
Yeah.
Mhm.
I have one more question in
Yeah,
spirit of
please.
Delius. So, Serge, I remember, I don't know if it was in your PhD or later on, I think you also studied not just graphs, but so-called ramified spaces.
Yes, exactly. Yeah.
And
Absolutely.
were there some progress in this area recently? Or?
So in my parts, no. I mean, I worked on this, well, let's say, for 40 years and 30 years ago, and then I stopped completely on this stuff. But recently, I received an email from an Indian PhD student that was interested in my work on that stuff. Yeah. So, but so otherwise, I don't work so much. I don't heard about that quite so. No. But well, maybe for other persons, I should explain what does it means. You see, the goal is, okay, the problem is that you, in a sense, you consider a graph where each edge is replaced by a polygons, for instance, yeah, and then you have, and the vertices becomes edges, yeah. Then you have a sort of books, yeah, and on each polygons you have a Laplace operator, and then along the edge you put some Kirchhoff conditions, yeah. And one challenging question at that time is that it was the regularity of the solutions of the Laplace equation simply, yeah, because it's a non-smooth domain, and that's the starting point for me to work on regularity of PDEs on non-smooth domains, because, well, I learned from that some PDEs could have solutions that are not H2, yeah, when the operator is of order 2, yeah. Yeah, but I don't know if some people has proved, for instance, Weyl's formula for such operator. This could be also quite interesting, yeah. But you have also applications in mechanics for such problems.
You see, I was thinking that maybe we should, to accomplish this, we can simply ask Serge to write, I don't know, something like 1 page of open questions. Because I like Delius questions, so it could be
Yeah.
to share it with other members of our
Yeah.
network, for example.
Yeah.
Yes.
But maybe we can share this page together and
Yes, sure.
we add maybe some other ones. Yeah.
In fact, let me maybe just add, there is, so our web page of the action is going to be launched soon. And within the page of the action, two of our members, namely Daniela Flimmel and Setena Ektuman, they had the great idea of starting a so-called collaboration hub. So some kind of collaborative subsection of the page where open problems can be posed and people can decide to join forces to start working and trying to solve problems. So actually, if you had a problem that's easy or kind of easy to be attacked by a large corporation, then probably it could be a nice attempt to start working in this way. I think also something to really enjoy the strength of this action as a whole. So I would be very happy to welcome your problems.
Okay. So when it will be opened or launched, this web page?
The page is already there, although it's not yet completely full. But this subsection of the page, the so-called collaboration hub, I think it's still work in progress.
Okay.
Maybe Daniela can comment if she wants. But otherwise, yeah, please, Daniela, go ahead.
Thank you for the advertisement.
It is true that we are, it's currently under construction, let's say the collaboration hub, but it could be open soon. Maybe Seth and I will know more. We are basically finishing some details. I'm writing an example so you could see how this would work. And we will let you know probably by email, and I'll be happy if it raised some interest from you.
Okay, very good. Then we're almost done, yes?
Yeah.
So let us thank Serge again, and
Thank you also for
yes,
your nice
and
questions and remarks. Yeah. Thanks again for the invitations.
it was very nice. Yeah. Okay.
Bye-bye. See you
Bye.
very soon.
And Delio, is there some meeting now? Or?
No, I don't think so. But in around 2 months, we will have a new
No,
Lumer lecture organized by another working group, of course, by working group number
okay.
2.
Okay. Then I misunderstood something.
Okay.
Okay. So
Okay. See you.
bye-bye.